this circuit, then we can go from right clockwise or anti-clockwise. If you give the direction, then we have two paths to reach from one vertex to another vertex from any two vertex of this circuit. So it means that here we get some vertices. Between that two vertices we have not a unique path, we have more than one path, but we have already proved that in a tree we have only unique path between any two vertices. So this way we get this contradiction. So let us see. So then there are two paths between every pair of vertices in the circuit C. That means graph G remains connected after removing any edge from C. Okay, so here we have give some different argument here. So here what we are doing, we are removing one. Here we are removing one edges from C, and let us say that edges is EI, be an edges in C. Then G minus EI is still it is connected graph with n minus 2 edges. If we remove one edges, then still it is connected. So here we are removing one edges, so edges becomes n minus 2, which is a contradiction with the fact that above previous result. Above result says that if we have n vertices, then tree contains n minus 1 edges, but here we have n minus 2 edges. So that is contradiction. Why we get this contradiction? Because we assume that G contains a circuit, but it means that G does not contain any circuit. So this implies that G is connected acyclic graph, and so G is tree. So this completes the proof of this result. Now we discuss minimally connected graphs, and I hand over to Dr. Gaurang Ghodaksara, who will discuss minimally connected graph.
Thank you, Professor Milan Kansagra. Myself, Dr. Gaurang Ghodaksara, working as an assistant professor in mathematics at HNSB Kotak Institute of Science, Rajkot. Today we are going to discuss about minimally connected graph, then types of trees like rooted tree and binary tree especially. As Professor Milan Kansagra has discussed the trees and various properties of the trees with the proof also that any tree is a connected acyclic graph. It has exactly n minus 1 edges provided there are n vertices in the tree. We start with minimally connected graph, the concept which is based upon the connectedness of a graph. First of all, let us start with what is minimally connected graph. Next please. Minimally connected graph simply means a connected graph which is said to be minimally connected if we remove any single edge from the graph, it makes the graph disconnected. Removal of any one arbitrary edge will make the graph disconnected. That is the idea of minimally connected graph, which suggests the name itself. Minimally means if you remove any one edge, it becomes disconnected. So it obviously says that minimally connected graph means every edge is specially a bridge. Now we have already gone through the concept of tree. That tree means it is a connected acyclic graph with n minus 1 edges, and we try to relate these two ideas basically, minimally connected and a tree. Now if you observe one thing, the remark what we have written is the graph is minimally connected if and only if it is a tree. Now if you observe the proof of this, once we start with any tree, let us start with a tree. It is a connected graph with n minus 1 edges provided that there are n vertices in the tree. Now if we delete any edge from the tree, the number of tree would be n minus 2, and if number of edges is n minus 2 for a graph with n vertices, then obviously it will be a disconnected graph, because of the fact that a connected graph will have at least n minus 1 edges. So a graph with n minus 2 edges will be a disconnected graph, and hence tree must be a minimally connected. So that way is quite easy to get the proof. The another part is starting with a minimally connected graph. We want to prove that it is a tree. Let us assume that suppose a minimally connected graph contains a cycle. In a contradiction part, we assume that minimally connected graph contains a cycle. If it contains any cycle, then removal of any edge from that cycle will remain again connected, because it's a part of cycle. So there will be a path in between any pair of vertices, so it will remain again connected, and that violates the condition that the graph is minimally connected. So that is a very easy and trivial proof of that remark, an important remark, that a graph is minimally connected if and only if a tree, that means tree is always a minimally connected graph. Now we go for the types of tree. The first very basic type of tree is a rooted tree. The definition is like this: a tree in which there is one vertex which is distinguished from all other vertices is called a rooted tree, and the vertex which is distinguished from all other is called the root of the tree. Taking few examples to understand this particular concept of rooted tree. Next, look at this figure as an example of rooted tree. The first vertex V0, which we consider as root, and especially if you go through the figure, V0 is distinguished from all other vertices, and it is situated at the first level of the tree. Then it generates the other vertices, and other vertices are joined by different edges, and other vertices are connected by the path from the V0, and obviously there will be a path from any two vertices, because itself is a tree. It's a connected acyclic graph, so there is no cycle in between. Next, taking few more examples of the rooted tree. If you see the first example, the central vertex will be represented as a root. All other vertices are distinguished from that particular root. In the next vertex, the bottom vertex is a root of this, and in the third, the top vertex is a root. So it is not necessary that the root is always lying on the top of the part, because the graph is completely different from the drawing itself. You can draw the graph in any ways. You can draw the rooted tree by any ways. It will represent a rooted tree with a special distinguished vertex which is called a root of the tree. Next, binary tree is a very special case of rooted tree. So that must be a root corresponding to this tree, and root satisfying certain condition. In fact, vertices of this tree will satisfy certain conditions. The conditions are mentioned in the definition, that it is a rooted tree in which there exists at least exactly one vertex of degree 2, and all other vertices are of degree 1 or degree 3. So basically, if you make analysis of this particular binary tree, there is exactly one vertex of degree 2, that means which is different from all other vertices, as far as all other vertices are of degree 1 or 3. That means the vertex of degree 2 will be considered as a root of that particular tree. So by default, the definition says that it is a rooted tree. The next line says that other vertices have degree 1 or 3, either 1 or 3. There is no other number for the degree is concerned. That means we have three types of degree sequence in this particular binary tree. One vertex with degree 2, and all vertices have degrees odd, either 1 or 3. So there will be one vertex of degree even and other vertices of degree odd. And this particular fact will put light on two different properties of the binary tree that we will see one by one. Especially, I told you, every binary tree is a rooted tree where the vertex of degree 2 is called the root of this binary tree. Next, properties of binary tree. The first one is the number of vertices in any binary tree is always odd. This gives you the characterization of binary tree in terms of number of vertices. You can recognize number of vertices of any binary tree, and that would be always an odd number. That means binary tree can be drawn only when number of vertices are given odd. For even number of vertices, binary tree won't be possible to draw. In case of the proof, consider any binary tree with exactly n vertices. Out of these n vertices, there is exactly one vertex of even degree, that is degree 2, and other n minus 1 vertices are of odd degree, either 1 or 3. Next. Now if you consider any binary tree, there will be exactly one vertex of degree even, that is 2, right, and other all vertices are of odd degrees, and there is a famous result in graph theory that in any graph number of odd vertices must be even. That means n minus 1 number will be an even number, because there are n minus 1 vertices are of odd degree. So n minus 1 will be an even number, and that's why the number n must be an odd number. That means the number of vertices in any binary tree must be an odd number. If you look upon the previous example, the examples of rooted tree, the third, the right hand side, top right side, the figure is given, which is a binary tree. If you observe this particular figure, the first vertex is considered as a root, the top vertex is considered as a root, and that root has exactly 2 degree. If you go to bottom, there are 2 vertices onto the next level, and both are having degree 3. In the next level, there are 4 vertices, and all 4 are having 3 degrees. And into the last level, there are 8 vertices, and all vertices are having degree 1. So if you observe this figure as a binary tree, the first vertex is a root, it is the only vertex with even degree, that is 2. And all the remaining vertices, that is n minus 1 vertices especially we call, they have odd degree, either 3 or 1. And if you count the number of vertices in this particular graph, definitely it will be an odd number. In particular, it is 8 plus 4 plus 2 plus 1, right? That is 15. So number of vertices in this binary tree is 15. And more specially, if you look upon the binary tree, if you look upon this example, we specially, you can represent the levels of this particular tree. The root, the topmost vertex is considered to be a root, and that root is at level 0. So at 0 level, the root is to be considered of degree 2. At the first level, all the vertices are considered of degree 3 for this example. It is not necessary to have 3 degree vertex in the first level. You may get any 1 level vertex or 3 level vertex upon the first level. If you go for next level, all the vertices of degree 3, again it is not necessary to get all the vertices of degree 3. You may get the vertex of degree 1 at the third level. Again in the fourth level, all the vertices, there are 8 vertices, all have degree 1, all are pendant vertices, right? Pendant vertices means a vertex with degree 1. So all vertices are pendant vertices. Again it is not necessary to have all pendant vertices onto the next level, fourth level. You can extend this also. At the fourth level, there are all pendant vertices. You can extend this tree to the next level also by just joining more and more vertices at the different level. If you go for the second figure, the mid figure, then you consider the level from the bottom. That bottom level would be the root, that is level 0. The next level is the level 1. It has degree 2 vertex. Again, you can repeat the same thing at level 3 and 4 and 5. So every rooted tree basically can be expressed into the levels. If you consider the binary tree, that what we have referred the example, the third figure, the top right figure, in that if you consider this, it is called actually a complete binary tree. Why is it called complete binary tree? Because at each vertex, there are exactly 2 vertex joined by an edge. If you observe the figure, at root there are 2 vertices joined. At each vertex at level 1, again there are 2 vertices joined by different 2 edges. Again at the next level, there are 2 vertices attached to every vertex onto the previous level. Now it comes to the fact that how many exact number of vertices will be in this tree, especially in this tree which is a complete binary tree. If you go for the level 0, that is a root, there will be a single vertex, we can express by 2 raised to 0. If you go for level 1, there are 2 vertices, can be expressed by 2 raised to 1. At level 3, there are 2 raised to 2 vertices. At level 4, there are 2 raised to 3 vertices. In general, at level k, there will be 2 raised to k minus 1 vertices in a complete binary tree. It is for complete binary tree. Next. Okay. The properties we were discussed, the first property we were discussed that number of vertices is always odd, and the proof we had gone through that since number of vertices we consider as n, it is divided into two parts. One vertex of even degree, n minus 1 vertices are of odd degree. Since n minus 1 is even number, total number of vertices must be an odd number. Next, the second property gives us the specific number of pendant vertices in that particular binary tree. Now if you refer binary tree, we have just three types of vertices. Number one, number of vertices with degree 2. Second, number of vertices with degree 1, that is pendant vertices. And third, number of vertices with degree 3. These are the different three types of vertices possible according to the degree sequence. We know the number of vertices of degree 2, that is exactly 1. Now we are here finding the number of vertices with degree 1, that is pendant vertices. If we can find this number, then obviously we can get the third number, that is the number of vertices with degree 3. So this particular property gives you the proof of the fact that number of pendant vertices in any binary tree with exactly n vertices should be n plus 1 by 2, and that number makes a sense because n is an odd number, so n plus 1 will be an even number and even by 2 is an integer, so that number makes sense. Going for the proof, let us assume that the number of pendant vertices in a binary tree with n vertices is p. P is the number of pendant vertices. Now recalling the fact of binary tree again, there is exactly one vertex of degree 2 and number of vertices of degree 3 will be n minus p minus 1. N is total number of vertices, p we assumed as number of pendant vertices, and 1 stands for one vertex of degree 2. So total number of vertices of degree 3 would be n minus number of pendant vertices minus number of vertices with degree 2, that is n minus p minus 1. Next. Now a very basic theorem of graph theory, that is handshaking theorem, says that summation of all degrees of the vertices must be equal to 2 times number of edges. So if here we make the sum of the degrees of the vertices, there will be one vertex of degree 2. So the first number includes 2 into 1, that is 2, plus p number of vertices degree 1, that we assume that p number of vertices of degree 1, that means p into 1 gives you a number p, and number of vertices of degree 3 is n minus p minus 1, so that number becomes 3 times n minus p minus 1. So total degree sum reduces to 2 plus p plus 3 into n minus p minus 1 in the last.